Okay, so next we're going to speak about IP spoofing. Of course, IP spoofing is obvious what that means, spoofing IP addresses. We're going to see what are the possible attacks and how can we defend against those kind of attacks in there. And I'm speaking about IPv4 spoofing. So now by default, network devices, switches, routers, firewalls, whatever, they don't perform validation of source IP address. So in a device which, like a layer 2 device, just switches a packet out there, a layer 3 device is going to do a lot of checks on the packet and look at the destination of the packet to route it, but it's never going to look at the source IP address. Now this allows for IP spoofing, which can lead to a lot of types of attacks. So clearly it's not good that anybody can, like pretend that, he has an IP address of whatever, which means he's going to claim other, let's say, another identity, which means there are a lot of attacks which are possible, and we explained those pretty much in the CCNA class. We also saw some of them previously when we spoke about the control plane policing part, where somebody was spoofing an IP address to generate a denial of service attack via ICMP unreachables. Now on layer 2 devices, like on layer 2 switches, we can prevent IP spoofing via a couple of ways. We can use a static port access list, also known as a PACL. We can configure IP source guard, which is going to be a dynamic port access list. We're going to see what that means. And also, of course, nowadays, ideally speaking, we're gonna have a dynamic port ACL, which is received as authorization via .1x or MAB HTTP or HTTPS authentication. So before this example is discussed in the SAS class. So ideally nowadays you don't need any kind of IP source guard or port ACL or port security, because all of those functions are embedded into 802.1x or MAB authentication. So if you control all access to the network via 802.1x and EAP and MAB, then let's say that framework has built-in MAC spoofing, IP spoofing, port security, and of course also authentication and authorization of the devices, which means also it's going to apply a dynamic access list to control traffic back and forth. But of course, let's speak about some old features like PACL and also IP source guard, since those are in the scope of the exam. Those are the options on layer 2 devices. And ideally, it's always better to, let's say, to drop the packets, spoofed packets, as close to the source, which means on a layer 2 device, it's not recommended to drop the packets, later on in the network. Why don't we just drop spoofed packets as fast as possible, which means as close to the source, which means on the layer 2 device where that attacker or whoever wants to spoof the IP or the MAC is connected. Now on layer 2 devices, we have a feature which is called unicast reverse path forwarding, or URPF, which is going to be likewise optionally configured so that those devices are going to perform some checks on the source addresses of the IP packets. Now PACL, to begin with, PACL overview and configuration. So PACL is nothing else but an extended access list applied on a layer 2 port, and only inbound direction is supported. Now I'm going to take a moment here to also again emphasize something that whatever you learn, it has to make sense. So I had a lot of, in many cases, people complain that, okay, why is this so complex? Why can't, things work in general and they work only like in the inbound or outbound direction? If you understand the scope of a PACL, which is used to prevent IP spoofing, which means is gonna do a check on the IP source, it means that it makes sense it can only apply in the inbound direction. Correct? I mean, if you look on that diagram in there, and this has an IP of 100 PC, and router 1 has an IP of .1, and if I put a PACL in there on that port, a PACL, it means I want to make sure that packets received inbound in that direction, I want to prevent spoofing with a PACL, which means I gotta make sure that packets received from the connected device have a specific source which I configure. I don't want that device to send packets or spoofed IP packets. So it makes sense that the packet can only be applied in the inbound direction, because I'm using it to prevent IP spoofing, so to control packets received inbound. Correct? So everything has to make sense in general. Configuration wise, it's very simple. You configure the ACL and you apply it on the layer 2 port. Now let's go next to the IP source guard. So IP source guard can filter IP packets based on the source IP address and optionally also based on the source MAC address. So it can filter them based only on the source IP address on the layer 2 source on the layer 3 source address, or on the layer 3 source address, which is the IP, and also on the layer 2 source address, which is the MAC address. Two types of filtering are available: dynamic and static. So source guard can build that filter either dynamically or statically. Now, dynamic filtering again relies on the DHCP snooping binding table, which means the switch is going to be able to dynamically prevent IP spoofing once I enable this capability for DHCP assigned addresses. Because hosts which are DHCP assigned, the switch is going to have a entry in the snooping binding table, and then the switch, when it receives IP packets, can check the source of that IP packets against the snooping binding table. Static filtering means that you have to manually configure static IP to MAC bindings, which is useful for statically assigned addresses like default gateways. So like if I want to prevent spoofing in VLAN 11, or if I want to prevent spoofing on this port of the switch and on this port of the switch, I gotta make sure that all packets received inbound on that port have a source address of .100 in that VLAN, and all packets received on this port have a source address of .1. Then for the PC, because I have DHCP snooping enabled, for the PC I can make use of the DHCP snooping binding database table, where in there I have snooping binding, because in the snooping binding table I have the IP to MAC to VLAN to interface binding for that host. So when I receive packets from that source in there, I'm going to be able to validate those IP packets to make sure that the IP address is not spoofed, the source address, by looking in the snooping binding, in the DHCP snooping binding, and I'm going to find in there what was the IP address which was assigned to that PC via DHCP. But for traffic received inbound from router 1, so for traffic received inbound from router 1, if I configure IP source guard also to prevent spoofing of traffic received from router 1, I cannot validate that traffic against the snooping binding table because router 1 has a static address. Which means if I want to prevent snooping in there, I have to go on the switch and create a static binding of IP to MAC to port to VLAN, so that when I receive traffic from router 1 source to .1 with an IP address of .1, I'm going to verify, I'm going to make sure that that the router 1 doesn't do IP spoofing by verifying the source of the packet against the static binding. Now, source guard configuration. So source guard requires DHCP snooping for the VLAN where you want to enable IP source guard. And it makes sense, because why would you go in a VLAN with all hosts being statically assigned? It's going to be a nightmare to go on the switch and statically configure IP to MAC to port to VLAN bindings just to prevent spoofing, right? So actually IP source guard does not even work. It's inactive if DHCP snooping is not enabled. And it makes sense. But now IP source guard is enabled at the port level, not at the VLAN level. And it makes sense because, for example, you may not want to prevent spoofing on all hosts, because maybe in that VLAN you have both statically assigned hosts and dynamically assigned hosts, and also the default gateway. So maybe you want to make sure that you don't have spoof packets in the network from the dynamically assigned hosts via DHCP, also from statically assigned hosts, but for the default gateway you don't care, for example. So this feature is applied on a port level, but if that port is in VLAN, let's say 100, DHCP snooping has to be enabled for VLAN 100. Otherwise, this feature is going to be disabled. It's not going to do anything. So as I stated, on the port where IP source guard is configured, which is known as IPSG, if the connected device has a DHCP assigned address, then the switch is going to IP to MAC binding is known from the DHCP snooping binding table. So the switch is going to be able to prevent spoofing by matching the received packet source address against the snooping binding table. But if the connected device has a static IP address, and if you enable IP source guard in there, the switch cannot validate that source IP address of the packet against the snooping binding table. You have to put a static IP to MAC binding on the switch to validate to perform this spoofing validation. Verification wise, you verify source guard configuration, show IP verify source, because that's what I'm doing. I'm verifying the source, right? So the command makes sense. Show me the IP verify source configuration. Or you can do it per interface, show IP verify source interface. And if you verify the dynamic and a static IP to MAC bindings via show IP source binding. So you're going to see in there the entries learned from the DHCP snooping binding table, and also the entries you have statically defined in there. So that's the IP source binding table. Now URPF, by the name, it performs reverse path forwarding check for unicast packets. So it's a feature which does additional checks to unicast packets. What checks? So this is a feature enabled on a layer 3 device. What checks is going to try to see what is the reverse path forwarding for that packet, which means how do I route for the source of the packet. So that's exactly what it does. Once you enable this feature, the layer 2 device is going to do a check against the source IP address of the received IP packet. We're going to see exactly how that works. So if on router 1 you enable URPF on this interface, when router 1 receives any IP packets on that interface, or a source of X, destination doesn't matter, router 1 is going to perform some checks against that source of the IP packet before allowing the packet in there, because it has to make sure that that packet doesn't use a spoofed IP address. Now URPF has two implementation options. We have what is called strict URPF, which is going to make sense, the name, what it does, and loose URPF. So the strict version is going to be a very strict check. The loose version is going to be a not so strict check in there. And we have two implementation options because each of them has let's say its own place in a network design. Now strict URPF overview. When a layer 3 device receives an IP packet on an interface with URPF enabled, it does a show IP route for the source IP address of the packet to find the egress interface. So that's what it means, that it is going to do a reverse path forwarding in there. It's going to say, okay, I got a packet of the source of X. It's going to say show IP route X, the source of the IP packet, to find the egress interface. And if the egress interface does not match the interface the packet was received on, packet is being dropped. So if we look in here, for example, so let's suppose this is our, let's say, what is our network? Our network is going to be this one in here. And let's say that this subnet in here is a public subnet. This is a public service, or not a subnet. Let's say this subnet. Let's say that this subnet is a public subnet, assuming that, because server A offers public services to the internet. So this is our LAN, and out there is going to be the internet, let's say. So that server A offers some public services, and let's say the subnet is going to be like 20, 20, 20, 0/24, where server A has an address of .100. And SHV is my border device facing the internet. Now, in a regular, let's say, without URPF, if SHV receives a packet inbound on this interface, source from 2020, 2020, destined to, let's say, 1010, 33.0. Of course, ignore the fact that this is not a routable address, which cannot exist in the internet, but let's assume that. So if ASH2 receives that packet inbound on this interface, ASH is going to say, okay, how can I reach the destination? It's connected to me. So destination is 30.30.30.100, let's say, which is PCA. So SHV is going to route the packet to PCB. Even if we look at the diagram, it's obvious that the source of the packet is spoofed, because that belongs to a subnet connected to the SA. And this is going to be one kind of an attack, because when PCB is going to reply, PCB is going to reply to actually a somebody in that subnet, right? It's going to reply back to the source of the packet, which is 2020.20.20. So a layer 2 device has no problem with this configuration by default, because it doesn't do any kind of checks against the source IP address, where it's obvious that in this case the source was spoofed. Now, if the same process, the same step happens, the same packet is received inbound on that interface of the ASA, but now ASA has URPF configured on that interface in strict mode. Then when ASA receives the packet, it says show IP route the source. It says it does a reverse path forwarding check against the source of the IP packet. It's going to say, how do I reach that source? By looking at my routing table. And the ASA then is going to see, well, that source, if I would route for that source, then I would reach it out on this interface, which this is the server nameth interface. So because the ASH3 would route for that destination, for that 2020.20.20, egress that interface of server, but the packet was received inbound on this interface, which is the outside interface, it clearly means that somebody has spoofed that's a spoofed IP packet. So chances are that clearly that somebody has spoofed the source to try to initiate some kind of an attack. So it's simple. In strict mode, when I get the packet, I say show IP route the source. So I get a packet inbound on gig 00 with a source of X. I say show IP route source of X. And if my egress interface it's another interface than gig 00, I'm going to drop the packet. I'm going to consider that that IP packet has a spoofed source IP address. So strict URPF prevents IP spoofing for known or routable IP addresses, because the device performing the URPF check has to have or needs a route for the source of the packet, but it has to make sure that the direction the packet was received with that source is the same direction that he would use to route for that source. Now, in strict URPF, legitimate IP traffic may be dropped in cases of asymmetric routing. So this is something you have to be aware of. Of course, if you enable URPF at the border of the network, like if you enable URPF, because that's what you do, if you enable URPF at the border of your network, there are less chances that asymmetric routing is going to happen. It can happen, it can be, but there are less chances. But if you, for example, I'm not sure, we can look at this. Yes, let's say that, for example, ASA3, so we enable URPF on ASA3, let's say on all interfaces. And let's suppose that ASA3 has a route for the loopback 0 of router 2, egress that way on this interface of gig 0091. So if we say show IP route on ASA3, that's how ASA3 would route for the loopback of router 2, which is 5552. Which means that if router 2 sends a packet to the ASA, but in this direction, let me use the color of radius. If router 2 sends an IP packet actually distant to ICE, but it routes it on the other interface, on the other physical path, on VLAN 38, with a source of 5552, destination of ICE server. Then clearly if ASA3 has URPF configured on this interface, it is going to drop the packet. Because this is going to drop the packet, because ASA3 received the packet, it received the packet inbound on gig 01 interface with a source, let me use the color of blue. It received the packet inbound on gig 01 with a source of 5552. But when ASA says show IP router source, ASA is going to route for that source egress to another interface. So ASA is going to believe that that's a spoofed packet, which actually it's not, because it's within my network, right? But because of due to asymmetric routing, it just happened that I'm going to accidentally drop legitimate traffic. So when you enable your RPF, you ideally going to do it at the border of your network towards the internet or the WAN. And you got to make sure that you don't have asymmetric routing in that portion of the network, because you may drop legitimate traffic. Now, loose mode URPF. When a layer 2 device receives an IP packet on an interface with URPF enabled in loose mode, it does a show IP route for the source IP address to see if it has a route. The egress interface is not relevant at all. If it fails to find a route out on any interface, the IP packet is dropped. Or if the route points to null 0, likewise the IP packet is dropped. Because in general, in a lot of designs, you rarely see a null 0 route on the border devices, because in general you're going to enable URPF at the edge, on the edge devices. Of course, it can happen that you need a static route to null 0 to inject that route into BGP or something else. That's another discussion. But in general, you're not going to have a null 0 route for something unless you want to drop those packets. And this second step, that if the route points to null 0, the IP packet is being dropped, is for a specific use case called RTBH. It's a BGP use case, remotely triggered black holing. So go ahead and read about this capability. It's going to make sense why, if a router has URPF in loose mode enabled and it receives a packet and does a show IP route for the source, and if it finds that it has a null 0 route for that source, it's going to drop the packet. So in loose mode, it's very simple. I receive the packet inbound on a loose mode URPF enabled interface. I say show IP route for the source, and if I have no route for that source, or if I have a null 0 route, I'm going to drop the packet. I'm going to consider that the packet has been spoofed. The source address has been spoofed. So the loose URPF prevents IP spoofing for unknown or bogon IP addresses, which is also the use case of RTBH, remotely triggered black hole filtering. Legitimate IP traffic will not be dropped in case of asymmetric routing, of course, unless you have a static non-zero route for other use cases. It can happen, but not due to asymmetric routing. So in loose mode URPF, you're not gonna get packet drops in case of asymmetric routing because you enable loose mode. Because in the previous use case in here, where the ASA had a route for the loopback curve router 2 in this direction, for the loopback 0 router 2, it had a route out there, and then it got traffic inbound on this other interface with a source of loopback 0 router 2. If ASA would run in loose mode, which we're going to speak in a couple, ASA doesn't support loose mode, but let's just suppose it does. If it receives a packet with that source on that interface where it has URPF enabled in loose mode, URPF enabled in loose mode, it's going to be no problem. Because the ASA in loose mode says show IP router source, and as long as I have a route for that source, I'm going to accept the packet. Doesn't matter if the ingress interface of the IP packet matches the ingress interface of how I would route for that source. So this means, as I said, that loose mode is used to prevent IP spoofing for bug on networks. There is an RFC written for that. So bug on networks are networks which should not be seen in the internet as a source IP address. IPv4 bug on RFC, or list, or the Martian addresses they are known as well. And these guys, you can even the team simv.org, you can even peer BGP with them too, so they advertise you what is the bug on list. So you should not see packets with those source addresses in the internet pretty much. That's pretty much a long list in there. So this is the scope, the use case of loose URPF. If this is your border network, let's say this is, because ASA doesn't support loose mode, so let's go and let's say this is my network, and out there is the internet. So I'm going to go in router 3 and enable loose mode on this interface, URPF in loose mode. So that if I receive packets inbound in there with a source of that bug on list, which means when I do show IP router source, I don't have a route for that source, then I'm going to drop those packets. So that's the use case of loose mode. So we have two implementation versions because we want to protect against spoofing. We want to prevent IP spoofing in different use cases. ASA and iOS URPF configuration, you just enable URPF per interface and that's it. And ASA supports only strict mode, as I stated. Only the iOS supports both of them. Verification wise, on the iOS you say show IP interface and interface number. So on the iOS, whatever you configured as an IP functionality is going to be verifiable with the show IP interface command. So whatever you put at the interface level, like IP unreachables, what else? IP unreachables, URPF, IP access list, in out, QoS function, for example, a couple of them. So whatever you put as IP feature at that interface level, you're going to be able to verify that with a show IP interface, the interface number command. ASA verification is going to be the verification on the ASA is it's better, it's self-explanatory. Show IP verify statistics, which means show me how many packets have failed the URPF verification.